All right, so we've learned about energy and work so far. Now, in this lesson, we are going to talk about how all of these concepts are connected and then add one more connecting concept in power. So we'll talk about power and the work-energy theorem today in this video. Our objective is to be able to describe and calculate the power generated within an object and apply the principles of the work-energy theorem. Your essential question that you all should try to answer in the end of your notes in about a 1 to 2 sentence summary is: how are work, energy, and power connected? So let's start off with something that we are already familiar with, and that is the concept of energy. So remember, when we talked about energy, and we learned it in one of our earlier videos, we learned that energy is defined as the ability to do work. So you all already are seeing a vocabulary term right here, and that is work. You also learned 3 different equations for calculating energy. We have this top one, which calculates the total mechanical energy. I always like to write total here to indicate, remember, that mechanical energy is the total energy between the kinetic and potential energy of an object. We also learned kinetic energy's equation, as well as how to calculate the potential energy of an object. And we also know that the unit of measurement for energy is the joule. So I'm going to scroll down here because the joule is going to be important for our topic today. All right. So that is pretty much everything we've learned about energy so far. And we also know that energy can be conserved, right? An object's kinetic energy is not going to magically disappear. It might be transferred to a different type of energy, such as potential energy. All right. So we can also go back and review what we've learned about work as well. And you'll notice that work is defined as the energy transferred to or from an object via an applied force over displacement. So we know that we can already calculate work by multiplying force times displacement. And I'll write that again. That's our force times displacement. We already know we can calculate work this way, but notice the definition of work is talking about a transfer of energy. And we also know that work is measured in the same unit of measurement as energy. So both work and energy are measured using joules. So we know just based off of this unit of measurement that these two concepts are connected. And that is where it brings us to this work-energy theorem. So you see, this is why I love these mind map notes. You can see how this is kind of bridging the gap between work and energy. So our work-energy theorem, I'm going to highlight this for you all. Our work-energy theorem states that the work applied to an object can either add kinetic energy to the object or take it away. So if you were adding kinetic energy or taking away, let me just be very clear. That kinetic energy isn't just disappearing. It's just being transferred to a different object. So kinetic energy is being transferred between 2 objects. Either way, if you were adding or taking away kinetic energy, we know there's been some sort of change in the object's kinetic energy, which leads us to this equation here. So this is our work-energy theorem equation. So the amount of work applied to an object, the amount of work done on or by an object is equal to the change in kinetic energy of that object. So you all have seen this sign before. You know, I told y'all this was going to keep coming back. All right, remember that's our delta, our Greek letter delta, which means change. Okay, so this is our main work-energy theorem equation. Now, to calculate the change in energy, we could go multiple ways. Maybe a problem gives us an object's two different energies. We might have a final kinetic energy and an initial kinetic energy. That makes our math super simple, and we could just calculate that change in kinetic energy by subtracting the two. Sometimes it doesn't give us that. Maybe it gives us a final and an initial velocity instead. So in that case, we have to use the velocity to solve for our kinetic energy. So what I wanted to show you all, this highlighted equation right here, this is our main equation that comes from the work-energy theorem. But in order to calculate the change in kinetic energy, there are multiple ways that you might need to do this. So that's what gives us these other two equations here. And I will go ahead and highlight those and bracket those in as well. All right, so we do have those two equations which can help us calculate work, but those are simply just there to calculate the change in kinetic energy. All right, last thing I wanted to point out related to the work-energy theorem is that we can have a positive or negative work. Now, remember, work is a scalar, so a positive or negative work does not necessarily indicate the direction the work is being done, but it does indicate something about the object's change in energy. So if there is a positive work, you are working through a problem and you see that the amount of work applied to an object is positive, then you know that energy was added to the system, right? We know that from our subtraction, right? If this final kinetic energy is going to be greater than this initial kinetic energy, that's going to give us a positive work. In contrast, if you calculate the change in kinetic energy or the work and it's negative, you know that energy was taken away from the system. So those are two other main points I wanted to add that is helpful to us from our work-energy theorem. All right, so now you all kind of get to see how work and energy are connected through the work-energy theorem. I'm going to go down to this new concept of power, and you will see that power is also connected to energy and work as well. All right, so power is defined at, we have two definitions really for power, and it's really just how you want to think about how they are connected. If you want to think about how power is connected to energy, we use this definition of power being the change in energy over time. So we will talk about how that kind of plays out in the equations in just a moment. Power can also be defined by connecting it back to work, and power is also defined as the amount of work done over time. So we see this play out in these two equations. If we are defining power as the work done over time, we can use this equation. Probably should get a little bit of a bigger highlighter here. All right, so we know from this equation that we are dividing work by time. But you remember there is also another way to define power, and that is defining it as the change in energy over time. So power can be calculated by dividing the change in energy by time. And I will highlight that for you all as well. So again, these two equations come from our two different definitions of power and honestly the work-energy theorem. Because remember, work and the changing kinetic energy, these are the same. Work and the changing kinetic energy are the same. That's from our work-energy theorem. Okay, so there you have it on how we calculate power. Now, power is, if you notice, the variable for power is a capital P. So nice and simple, power starts with a P. So we're going to use a capital P to represent power in all of our equations. Our unit of measurement for power is the watt, and you might be familiar with the watt. We've learned a lot of different units of measurement, but the watt is actually one that we use a lot in our everyday lives. So if you have an 8-watt light bulb, right, that is a way of describing the power of the light bulb. And another cool thing to note is that 1 watt is equal to 1 joule divided by 1 second. So this is how we get our unit of measurement, the watt, is by dividing some of our other units of measurement here. So a joule divided by a second. Remember, joules measure both energy and work, and over seconds, which measure time. So you can kind of start to see how that unit of measurement is connected to those equations there. All right, lastly, we will wrap up this video by showing a demonstration of how we might calculate the power of an object. All right, so here's our example problem. Michael Phelps does 60 joules of work to swim 500 meters in 20 seconds. So as always, we are going to follow those 4 steps to solving a physics word problem. So I'm going to draw some water here. Here's Michael Phelps in the pool and swimming. All right, that's pretty simple drawing. Apologize for my stick figure drawings. All right. But another thing I like to draw out is some of these numbers here. So we know that his work is equal to 60 joules. All right. He swims 50 meters. He's going to swim 50 meters. And his time is 20 seconds. So he's moving pretty quickly. All right, so that is my step number 1 to solving any physics word problem. I've drawn out the problem and I've written and labeled that picture a little bit. So we're going to move on to step number 2, which is making our T-chart. So separate what you know from what you don't know. All right. And let's go through the problem again. Really quick trick for figuring out what you know and what you don't know are simply to look for the numbers in the problem. So first number I see is 60 joules of work. So I am going to write in my no column, W is equal to 60 joules. Okay. Swim 50 meters, but let's back up for a sec because this is a number that we know, but let's go to what we are supposed to find out. Let's talk about what we don't know. So this problem asks to calculate Michael Phelps's power. All right, so I know I'm solving for power. So I can put that in the I don't know column. All right, and you'll notice if we're just keeping this stuff in mind and looking to step number 3, looking ahead of ourselves here, there is nothing in either one of these equations that asks for Michael Phelps's distance or displacement here. All right, so what I want you all to realize is that this 50 meters in the problem is really just to throw us off. It is not a number that's going to be super useful to us. We can go ahead and write it in our no column because we do have that information from the problem. But just note that we might not necessarily need all of those numbers that the problem gives us sometimes, all right? And moving on to the last number from the problem, you can see that we have 20 seconds. So remember, seconds measures time. So I know that his time is 20 seconds, right? So that is a completed T-chart for step number 2. And we can go ahead and move on to step number 3, which is making our equation. So again, this is where step number 2 becomes particularly important when we're calculating things like power, because we actually have 2 equations we could pick from. So we need to look at, I'm going to keep our equations in the top right corner of the screen, look at our 2 options for those equations, look at our step number 2, what we know, and using what we know, we need to pick which one of these equations is going to work best. So I want you to pause the video, think for a second. What equation should we pick between these 2 power equations based off of what we know from the problem? Now, hopefully you all came to the same conclusion that I did, which is we are given work and time. So that gives us this top equation as our best option here. So we are not given anything related to energy. So I'm going to write out our power equation, which uses work and time. We've got the equation is set up correctly. We've got work and time over here. So I should be good to go ahead and start plugging in those numbers and solving. So as a reminder, I'm going to plug in my number for work first, right? And we know from the problem that Michael Phelps does 60 joules of work. And I will add that division sign back in. And then we will go to our time, and plug in time. And we know that Michael Phelps completes this in 20 seconds. So this gives us our power equation. And to calculate power, we're just going to ultimately end up dividing 60 by 20. So if you all plug that into your calculator, 60 divided by 20 is 3. And remember, our unit of measurement for power is 3 watts. So that is our final answer for that example problem solving for the power of Michael Phelps. Right, so I hope that this video helped you all understand and make some connections to some of these concepts between energy, work, the work-energy theorem, and this new concept of power. Please remember to write your summaries at the bottom of your notes, trying to answer that essential question. And I look forward to discussing this with you all more in class.